Alright guys, so in this video um we'll be considering residues at simple pole and at ordinary pole and at end poles. So we have a Laurent series A0 plus A1, then we have our residue to be A minus 1. So our residue is the coefficient of z minus z naught raised to power minus 1. So that's the definition of a residue. Now, the Laurent series can also be written as the sum of z naught, z minus z naught raised to power n plus a minus 1 z minus z naught plus sum of n equals 2. Of course, we have a minus 1. After a minus 1, the next one should be 2. Then when we integrate all the sides with respect to z, we have our integral to be that. We have our integral to be sum of an integral of z minus z naught all raised to power n dz. Then we bring out the a minus 1. So we take the integral of the z over z minus z naught plus dot 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 sum of n equals to 0. Sorry, this other part where I inserted n equals to 0 is meant to be n equals to 2. So kindly change that. So we have it to be integral of a minus n z minus z naught. And for all integrals, since z minus z naught is analytical, that is, it has no denominator, so automatically z minus z naught becomes 0. That is, integral of z minus z naught raised to power n dz becomes 0. Similarly, for integral of z minus z naught is a minus n over z minus z naught, that as well becomes 0, because whenever n is greater than 1, we have the integral. The integral becomes automatically what? Automatically 0. So we have our integral fz dz equals to 0 plus a minus 1 plus 0. Then we make a minus 1, and of course we know that a minus 1 is our residue. So in this case, we make our residue the subject of the formula. So this is the full definition of what a residue. But we'll be considering the residue at a simple pole. Now, to find the residue at a simple pole, what we need to do is to recall that when you take an integral of the z over z minus z naught, it is 0. The integral is 0 if and only if n is greater than 1. But if n is equals to 1, you know what n is. If n is equals to 1, the solution will become 2 pi I. So the solution is 2 pi I. Then you take the integral of fz dz. That's 0 plus a minus 1, 2 pi I plus 0. So you take the residue. The residue will therefore be 1 over 2 pi I integral of fz dz. So therefore, residue at simple points becomes, we already multiplied through with fz. We already multiply with z minus z naught. So we have our residue at simple points to be the limit of course, after multiplying with z minus z naught, you take the limit. Take the limit from z to 0 of z minus z naught f of z. Then we have it to be equals to the sum of limit of z minus z naught raised to power n plus 1 plus our residue. So at the end of the day, we arrive at z minus z naught times f of z. So this is the z minus z naught f of z is referred to as a residue at a simple point. So that is the residue at a simple point. That's the residue at a simple point. So we also have residue at n poles. That is when n is greater than 1. So residue at simple poles simply means when you have n to be 1. But residue at other poles when n is greater than 1. Do you understand? So we have it. So similarly, we have our Laurent series, but in this case we multiply f of z with z minus z naught, all raised to the power of n. And of course, a minus 1, a minus 2, a minus 3, they have the power of 1, 2, 3 respectively. So when you multiply with z minus z naught all raised to power n, we have the first one to be raised to power n minus 1, the second one to be z minus z naught raised to power n minus 2, n minus 3, and so on like that. Then we differentiate. Now if you have to differentiate 6z squared, differentiating 6z squared will give us 3 factorial. So similarly, differentiating n minus 1, the power of n minus 1 will also give us n minus 1 factorial. Then we take our limits, then we have our residue at ordinary point to be given as 1 over n minus 1 factorial, the limit of z to z naught, the n minus 1 over dz n minus 1. Thank you.